Hello and welcome back to the Oxford MAT Submissions Test livestream. My name's James and today, coordinate geometry, hooray! So, here's how the show works in case it's your first time joining in. If you've been to the Wednesday open day and you've just found out about the MAT Submissions Test livestream, then this is the most recent one, so here it is. Here's how the show works. There's a single website which you're encouraged to visit not only when we're live, but also before and after if you like. That's where we post these worksheets, which is the thing up the top. That's where we put solutions as well. So if you want to get solutions already, you could be looking at next week's questions and next week's solutions before the show. And the live stream is supposed to be a bit like office hours where we do some maths together. And I say together because I am joined by all of you over in the live Slido. Let's switch that on. Here you are. It's just Rex and Matty in chat at the moment, but we'll say hello to people joining in as we go. There is a link in the YouTube description or on the homepage, or if you go to slido.com and put in the event code MATLIVE, then you can join all of these people, like Dev and Extremal Combinatorics and Sky and Lala and Ginger Biscuit and Connor Sheen and Sam and Callums as well. And Daisy and Mary is here as well. Good to see all of you. Hello. How's your day going? How are you today? Let's do that poll. So the Slido is helpful because we do voting live, as well as people telling me hello and so good to see you all again. How are you enjoying the weather? Is it going all right where you are? In Oxford, it is extremely hot at the moment. Lots of places in UK and Europe are really warm right now, but Oxford seems to be right in the middle of all of the extreme warnings every time I'm showing one of them. Some people are having a terrible day. Is this one of the things that we vote on? Really, 12% of you having a terrible day already. That's quite high. Sometimes we do this poll and it's like 4 or 5 stars. I wonder. Yeah. Rex asks if we've got AC. Sadly no. Although AC is pretty terrible if too many people have got it right. But the maths department, I want to reassure people, this feels like advertising now. The lecture rooms downstairs are really nice. Basement, underground. Also, there's some system, it's not AC, but there's some sort of passive system that just makes them much more pleasant. My office, not so nice, but it's more of my problem. Hi to Isla as well, or possibly Isla. No, I'm going Isla, like the start of Island. Right, okay. So we're somehow down to a few people having a really terrible day, possibly extreme heat. Ginger Biscuit has no water in addition to too hot, so it's pretty bad. Ginger Biscuit is here reminding me, of course, that you don't have to put your real name in Slido. 2 things to say about this. 1, you can stay anonymous if you like. 2, you can set something else as your username if you like. People have been using that to set their names to their favourite biscuits or their favourite maths or their favourite mathematician. If you have been wanting to try out a different name, this is quite a safe way to do that, isn't it? You could just try out a different name and then I'll address you as with that. Right, okay. Sadlers is here as well. I don't know if that's Sadler's real name, but hello, Sadlers. Right, good, okay. Good, 4 and 5 stars in drawing. The average is 3.7, which is super low. People are not having a good day. We usually start with some maths. 2 things to do for this. I'm going to show you something slightly different about the worksheet, about the revision notes. And also I'm going to give you a challenge question, so that if you've already looked at the revision notes, then we've got a thing to think about. Okay, so down here, I've got a fact from the notes. Let's make that a little bit larger. A fact from the revision notes. It's, I think, from GCSE mathematics or something, or equivalent. The diagonals of a parallelogram bisect one another. Some of this stuff sort of, it feels like it's sort of, poetry is pushing it, right? But there's sort of some of the, you have all these lovely words like bisect and parallelogram. Oh, great stuff. Anyway, so here's a parallelogram, and here are its diagonals. And the fact is that these bisect one another. And my challenge question is to prove this. Okay, so maybe you're thinking about that. You've got the question, parallelogram, diagonals. Their diagonals bisect each other, so you're trying to prove that these 2 bits of line are the same length and these 2 bits of line are the same length into this middle point. Okay, That's the challenge. Let me draw attention to something that's going on over here. Okay, so poll, I'm ending the poll at 3.6. It's got a historic low, and one star has gone up to 14%. People are having a terrible time, even though Napoleon Bonaparte is here and says geometry, my favourite. Napoleon, people might not know in chat. People can work it out. I said famous mathematicians. Napoleon Bonaparte shows up and talks about geometry. People can join the dots, can't they? Right, okay, I want to show you the revision notes. Chat's going to vanish. Oh, something within GCSE maths this year, says Anonymous. There you go. Right, okay. Anonymous, brilliant, okay. Here's how I'm going to do this. I'm going to switch to this view so we can see this. I'm just going to hide chat briefly. So revision notes. We've always got this section at the top which looks at the TMUA specification, which is broadly speaking based on the first half of A-level maths, more or less. I've copied it out each week so that you can have a look at the language that they use in there, and so that you can get a list of, for example, all of the circle theorems that the TMUA specification thinks that you know. It's good to know, right? Because any of those circle theorems could turn up in a question at any point. And it won't just be, presumably, do you remember this circle theorem? Multiple choice, yes, no. There'll be something happening with it as well. We're going to see some of that today. Unusually, I have decided to include some bullet points from the GCSE part of the TMUA specification. So that's this. I'm doing this because I think for geometry and trigonometry, there's a few things that people might not have, fully taken to heart at GCSE. Just personal experience of talking to people at A-level. It's partly the circle theorems above the line, but then also there are some of these things like properties of parallelograms, which somebody in chat just said was on their GCSE maths exam, but that stuff just doesn't come up again at A-level for most people. I don't know, maybe you're doing an international qualification that is all about parallelograms afterwards. Properties of kites. Some of this stuff might be the things that you knew when you were 15 or 16, but now you're 17 or 18 and you've had enough time to forget it. And this is me saying, hey, look, I've picked 7 of these bullet points as things that you might have forgotten. If you think you've forgotten half of these, all of these, then these are selected. You should probably go and look at the others. There's a big long list of sort of other GCSE geometry facts in the TMUA specification. If you think that you've forgotten some of that, then you might want to go and look at the list. There is a link, of course, on the homepage, so you can find that. The properties of parallelogram include the parallelogram law. I think that's Ginger Biscuit showing off that they know a parallelogram fact. Right. Is a square a parallelogram, says Leonard Euler in chat. Hey, this is good. I'm putting chat back on. Okay, so I just wanted to highlight that unusually for this week, they're not all like this, but I've included some GCSE content, including possibly this parallelogram fact. The revision notes have sort of been expanded to include that. So if you're looking for a big long list of what the circle theorems actually say, here are some circle theorems with diagrams. So you can get these on the homepage. You might also like the flashcards that we've made, where you essentially see a diagram on one side, and you have to stare at the diagram and think, oh, which circle theorem can I use, and what can I conclude about this diagram? So if you imagine this one at the bottom, but without the angles marked. So the challenge is you see a triangle and a tangent line, and you have to think alternate segment theorem, those angles are the same, because that's using it without being told to use it. Those flashcards are also mixed together with lots of other topics. Anyway, right, okay, let's put chat back on and have a go at this question. So I'm going to scroll past some, here are some facts about parallelograms, and then, oh gosh, lots of facts about vectors. I think these might be the longest revision notes out of any of the worksheets that we've had so far. It's about 4 pages of stuff, isn't it? And we will come back and do some revision questions in a moment. But I'm just going to scroll back up here. Sorry to bounce up and down. Scroll back up here so that we've got the parallelogram fact at the top, just in case. And I'm going to go into split view. Quick look at chat. What's chat up to? Thank you, by the way, to Sonia, who's a current master's student and is in chat. I imagine somewhere in Oxford, maybe, in the extreme heat. If you're watching, Sonia, thanks for moderating chat. which means things can appear in chat. There we go. Could you do it by saying the angles are halved? Ah, interesting. Is that true though? Interesting. If it's true, then yes. If it's not true, then no. I'm worried. Am I worried? Yeah, I think I am worried. Yes. Okay. What else can I see? Could a square be a parallelogram? I think a square is a parallelogram. Special sort of parallelogram. This sort of question depends how you define squares and parallelograms. Sorry, I know this like horrible black bar appears when I start interacting with chat. It's not pretty, but that's just how my chat setup works. It's there in case I want to, I don't know, hide chat entirely or something. So symmetry, sort of rotation, you're going to need to convince me that that actually like works, that gives you the right things. The GCC math. So that's just the word bijective. Says hi. You can go for adjectives as well. Right. Okay. We got some ideas in chat. What other facts about parallelograms are we allowed to assume? Yeah. Right. Okay. So luckily I've got my parallelogram fact at the top. I think a parallelogram is a quadrilateral, 4 sides, where both pairs of opposite sides are parallel. Now, formally speaking, if we're playing this game properly, then that's the only thing you're allowed to assume about parallelograms. I should let you use some sort of toolkit stuff, some other things that you know about angles at a point or angles on a line, or the way that when a line crosses parallel lines, you get corresponding or alternate angles. I think that's on here as well. Is that on screen? No. Is it on the previous page? No. Is it on the next question sheet? Next sheet? Whatever. Okay. Ooh, vectors is an exciting way of proving this. I think you can use vectors, Sebastian in chat. You'll need to be a little bit careful about what you say these vectors are, but vectors are a really good way of describing parallelograms because, well, when things are parallel, you can use the same displacement vector. Anyway, here's how I would do this. You don't have to agree with me. So my aim, and this will be a 2-step process, I think, in the end, but if I'm being honest, I had the idea first, and then I worked out what the steps were. That's quite hard to communicate, by the way. It's really hard in a textbook or in written notes or something to say, I had this idea and it didn't work because I needed to fill in another detail. So I'll present that later. This is not the order that storytelling normally happens, but I'm giving it a go right now. It is about 30 degrees. Why am I going for alternative storytelling? Let's just roll with it. Idea. These triangles are similar. That's not really an idea, is it? That's just kind of like something you might think to yourself. Idea is maybe pushing it. Can I prove that? I think I can prove that. So I've got like this diagonal line. That's crossing a pair of parallel lines. So I have things like let's make that a nice, more pleasant color. I have things like alternate angles. I don't know if people know that word, but just in case, I'm going to also phrase it as the Z-shaped ones, where you see this Z shape involving parallel lines, and you get matching angles. That's a surprise to you. I think people find it less surprising that the corresponding angles, so this one up here, is the same. They're parallel, right? So this angle between the line and parallel, and then it's also the same angle between the line and parallel. But then, opposite the point, you get this angle here, which gives you the Z fact. I think that one is sometimes called like F or something, like alternate angles, whatever. The fact that this angle down here agrees with that angle up there, whatever. Presumably at some point you knew all of these. Aha, right, okay. Yes, chat is playing along. Brilliant. Okay. Very nice. I should look at chat more. Chat's going really fast. Well done. Chat is already talking about congruent triangles, which I'm being honest and admitting that was a separate idea for me. I don't mean similar, I mean congruent, but I'm going to get there in a moment. Similarly, these ones are the same. And then I've got angles that are the same in these triangles. So, yes, true. but then realization, but that's not good enough. Oops. Because similar triangles might be different sizes. This is a point we're maybe going to hit today. Similar means that the triangles have the same angles. Congruent means they have the same side lengths. Those are not quite the same thing. Similar triangles, different sizes. Okay, maybe the same size. They really are congruent. And these ones are similar, but they turn out to be congruent as well. Okay, so new idea. This is the two-step thing that I'm trying to demonstrate. I don't know. These triangles are congruent. And for me, that was two ideas, right? First, hey, are they similar angles? Angles are easy to check. Yes, brilliant. Second idea, are they actually congruent? Because I actually need that. If I want to say that these lines are the same length, colouring is hard. If I want to say that these lines are the same length, then I need the scale factor to be 1. I need them to have the same lengths. Ooh, other ways of saying yes. Okay, right. Chat's going for ASA, which is one of the congruence rules. We've got loads of those next week in the trigonometry section. Maybe I should merge these. It's already 4 pages though, so sort of quite a lot of stuff. No, there should be 2 sessions. We're going to do it like this. So sort of ASA for congruency, angle, side, angle. If that means nothing to you, then check next week's trigonometry notes, which have already been released. You can go and look at those. So we've got angle, angle, angle. That shows similarity. The suggestion in chat is that these sides are the same length down here, that this side is the same length as that side, which would be enough. We would then be done because angle, side, angle, like this, green, purple, pink, angle, side, angle, gives you congruent triangles. We would then be done. So I guess there's like a sub idea. Angle, side, angle. Here's the separate question then. Why are the opposite sides of a parallelogram the same length? It's sort of obvious, but it's not my definition of a parallelogram up the top there. My definition of parallelogram says both pairs of opposite sides are parallel. Oh, and I have put a note up there to say, oh, each pair of opposite sides is therefore equal in length, but I haven't told you why. Maybe that's fun. Maybe that's fun to think about. Do I know the triangle congruency rules song? No. I have a feeling I'm about to learn the triangle congruency rules song. Other 2 sides are parallel. Yeah, right. It feels like that's the important thing. The other sides are parallel. So which fact are we using though? What's going on there? And if we're doing this like an ancient Greek, then we need to actually use one of the rules, like similar triangles or something, in order to do this. Sky would use contradiction to show that they can't not be the same length. Fair enough. Okay. So I would do over here to show you that first fact in the bullet point up there, to show that they are the same length. I would draw a slightly different diagram. Oh, there are some vectors in chat. There are some slightly. I have feedback on the vectors where you are comparing coefficients of vectors. I'm going to put it on screen. I feel bad sometimes when I'm like poking holes in something, putting it on the screen. But the extremal combinatorics question, they would like to conclude that k equals 1. I don't think that's obvious that it follows. Maybe you're comparing coefficients or something. You're using some rule of vectors, right, to compare 2 statements and say that k equals 1. Yes, okay, right. Leonard Euler is up for some angles, living up to the chosen name there of Leonard Euler to tell me about geometry. Right. Yeah. So it feels like this should be a distance fact, right? And in fact, it's true. So maybe it is. It is true that opposite sides of parallelograms are equal length. The nicest way I know to explain why, though, is something like, I'm trying to use 4 colours today. That's a bit awkward. You have these angles, and you also have these angles. So these two triangles on opposite sides really are congruent. So I'm using more angle facts and parallel lines because really all I've got is parallel lines and angle facts when you really get down to it. These triangles are congruent, not just similar, because they actually share an edge, that diagonal down the middle. They actually share that edge. This means that we have ASA for those triangles, angle side angle. I've been instructed to look up the triangle reason and so on. Ah, right. Anonymous says that's what I said. Sorry, maybe I missed it. Aha! Yes, you know they're congruent because they share a side. There you go. Right. Okay. Yes. Well done, anonymous person. Good. Anyway, so what does this mean? If they're congruent, then the other sides are also matching lengths. So opposite sides are equal lengths. This nice tidy thing. If your argument in chat is some sort of symmetry or rotational symmetry, then I am medium convinced, I think I'll say. In an interview, I would ask you more about what sort of symmetry you are using and why you know the shapes have that symmetry, which will probably end up getting down to some sort of congruence thing or similar triangles or some angles in there somewhere. This is tiny writing. This is terrible. Whatever. I've said it out loud as well. Opposite sides are the same length. And then that fact combined with the thing on the right means that, hooray, they bisect one another. Those congruent triangles mean that these are congruent triangles. Oh my goodness. What a lot of congruent triangles. Good fun. Okay. So the question in chat seems to be, can you do it with using vectors? Where I think maybe, although you're going to need some vector facts maybe. Not obvious to me anymore. Yeah, you should be alright, shouldn't you? You can, it's coordinate geometry, you can find out where everything is. Yeah, I reckon you're fine. You can work out the coordinates of this point. Being something like, well, so even if you don't like vectors, you could write down expressions for the corners of this parallelogram without loss of generality. Let's say it's got the origin over here and A0 over here and BC over here for other points, and then work out where this is. Even if you don't like vectors, you can infer where stuff is, and then you can work out where the middle is, and it turns out to be bisecting both diagonals. So you can remove all the mystery by just giving names to all of the corners if you like. Yeah, okay, vectors works, or just bashing away with some coordinates. Welcome to the coordinate geometry session, where you have the option to bash away with coordinates. Anyway, I thought that'd be a fun intro to just see if we could remember some GCSE maths together, or equivalent. If you did an international qualification where all of that stuff comes up all the time when you're 16 and all the time when you're 18, then lucky you, I guess. In the UK, my experience is that people learn a bit of this age 16 and then tend to forget a lot of it. And it seems to be on TMUA, slightly. Not exactly that question, but there's a question coming up later, perhaps, if the audience vote for it, involving a kite, where just to get started, you need to know a property of a kite. It's on screen now. Right, good. Okay, let's do some revision questions, shall we? Oh, some sort of a cosine rule. Yeah, I'm up for some sort of a cosine rule. Okay. Right, okay, you know the drill if you've been here before, but otherwise, here's how it works. We've got some revision questions. This week there is a choice of 15 of them, including a new one that I wrote this year. Mostly I've been using questions from the old Maths Admissions Test live stream, but remixing the session slightly. This time, there's a new one in there as well. I always let chat vote. I don't promise to do all of the questions that people vote for. They can vote for multiple options, but I would like to let them vote. So voting's underway. I'm just going to hide it so that I can put the questions on the screen nice and cleanly for people watching without the revision questions, but you could go and get them on the website. Am I explaining the show too much? I think I might be explaining the show too much. No one's asked me to explain the show, which probably means, yeah, it's not enough. Right, okay. So there's some stuff at the top about equations for lines and things, which I've included. Some of this is left over from many years ago when we wrote a single page of revision questions just to check, like, have you learned this material at all? If not, then you're not going to be able to find the equation of the line through 2 points. I think that might be GCSE maths or equivalent, whatever. Here's a circle. Here's a slightly harder circle. Here is some angles and circles that are intersecting. The question 6, is that going to win? Oh, question 6 about the area inside both circles is pretty tricky. I've tried to make it so the angle's nice at least. 7 and 8 are both pretty hard. They're doing right in the voting at the moment. 9 is the new question. It's coming third right now. And then 10 and 11, check that these are a square or a trapezium. What do you need to do to check that something is a square? Like, how do you know it's a square? Check that that square is square-shaped. And then finally, fact about kites. If you want to do a similar question that's a bit like the one that we just looked at. Make me a triangle, and there's a vector stuff. And at the moment, the vector stuff is winning. Oh, no, it's now tied. I'll let more people vote, I think. Voting is fun. Right. Why does congruent mean the diagonals must bisect each other? Ah, right, okay. So, first part, I had a pair of congruent triangles on the left. Whatever, I'm going to put it back on screen. We're split. There we go. First part, for this person in chat who's asking for it one more time. I had a pair of congruent triangles on the left that convinced me that the opposite sides were equal lengths. There's a fact here that it feels like magic when you really think about it, that if you know angle, side, angle match for a pair of triangles, then the other two sides match as well. Like, you don't have to calculate them or look at them or think too hard. You just get to say, for free, those other sides are the same length as each other. So even that data is only about one of the sides, but if you have angle, side, angle over here, so the green angles match, the purple angles match, there's a side in the middle. Oh, that means the other pairs of sides also same size. Weird. And then there's a second argument in here, looking at these shaded triangles, where again we've got angle, side, angle that agree in these two triangles. It's different angles and it's different sides, but the same rule. If you know angle, two angles and the side in between, then you get to deduce that the other sides must match up as well, same length. You don't even have to like calculate or use the sine rule or anything weird like that. And the corresponding sides here are the one next to the green. Oh no, sorry, the one opposite the green angle. That's over here. That matches up with the one opposite the green angle in this triangle. They must be the same length because those triangles are congruent. They're the same shape and the same scale as each other. Ooh, slightly nasty shorthand there. I regretted saying that. Similarly, this line opposite this side of the triangle opposite the pink angle matches up with this side of the triangle opposite the pink angle. So those agree as well. It's just quite cool, I think. Once you know triangles are congruent, you know the sides that you haven't calculated yet match up. Which maybe is the thing that you're being asked to do. Congruent triangles. Very good. Right, okay. The voting looks like this, which is question 9, question 8. Hooray! Oh, I mentioned question 9 and then people voted for it. Hooray! And question 6. Oh, the area inside both circles. Yeah, kind of predictable. A little bit of 7 as well, which is fair as well. And then I see 12 down there as well about the kites. Okay, fair enough, I think. Exactly 34 votes. Is question 6 similar to that one Edexcel question? There is that one Edexcel question. I think it is the same sort of setup. Let's do a really quick behind the scenes on question writing. I think it's got something in common. I know this isn't the way the vote went, but I'm going to do it like this. Full screen. No chat. Okay. Question setting. Kind of natural thing to ask is to have two circles that overlap each other. Because you've been trying to write questions with one circle, you think 2 circles, hooray. And then what you get some area in between if they overlap. So the kind of natural question is like, how big is that area? And then the problem is that this question turns out to be quite hard. And if you want to actually go do this, in general, for a pair of circles, then it's really hard work. So in order to make this into a GCSE question, what you might do is you might try and simplify things. For example, you might make the circles the same radius. If you make them the same radius, then you might as well line them up like this. But still, there's some complication by having like the angles involved. You've got to work out what these angles are. It's pretty hard work. So there's one further simplification that I've seen people make lots of times, and I've done it in this question as well, which is that you make the centre of each circle lie on the circumference of the other one, which sounds super random. Have I done that well? I've not done that very well. I'm just going to... You saw nothing. There we go. The centre of each circle lie on the circumference of the other one, which the first time you see it sounds like what? The centre lies on the circumference both ways round? Like, it's completely mad. But once you've seen it a few times, you realise that that's come up. Once it's come up a few times, you've got this maybe picture in mind where you could do this. So that the centre of the left circle just happens to be on that one. This is a nice setup. The thing that you're supposed to do when you do this is like drawing some radiuses if you want to, and drawing some extra lines if you want to. There are no rules about how many of these lines you draw, but I like to draw a few lines. Has it become obvious what's going on yet? Maybe not. Everything's equal. These are equal because they're radiuses of the left circle. These are equal because they're radiuses of the right circle. Oops, equilateral triangle. So that's 60 degrees. And there's loads of 60 degrees going on. So here and here and here and here and here. So this nice setup where you take this kind of ambition to do a question where you say, I've got two circles and they intersect, tell me about the area. And you get, loads of 60 degree angles. And kind of rewards you and makes the question actually doable. Right. Okay, Connor has realised that question 9 is like a clock. Good. Okay. Adam wants to know if I have less work or more now that there's no maths admissions test. Actually, that's not what they say at all. They phrased it differently. I've got so much work, it's amazing. Don't worry about me. There was a point where I thought rebuilding the entire MAT Livestream into TMUA focused would be really easy, and then there's the desire to write new questions like this one. I am finding things to do. Right, okay, let's use the circle tool again. So this question is a bit like a clock face, a bit of a running thing for me. I've done this with a few questions in my life, I suppose, where I've got 12 equally spaced points around a clock face. I suggested a question like this in the office for a different project recently, and my colleague said, James, you can't suggest any more clock questions. Stop making everything be about 12 equally spaced points around a clock. But hey, the nice thing about 12 is that it's one of the factors of 360. And it reminds people about clocks, right? So that's nice. Good. Ooh. I think I've done everything correctly. There we go. Good. Oh, right. Okay. So, Connor in chat wants me to connect the points A, B, C to the center of the circle. And they say you're going to form a kite. I can't immediately see the kite. Do they mean kite? Maybe. So I have points A, B, and C. I connect them to the center of the circle. I think that's already clever because it brings in lots of angles, and the center is often relevant to a lot of these circle theorems that you've learned. So what's the question say? The question wants possible values for the angle ABC. Martha wants to find the area of segments. Interesting. Yeah, right, that's how you would do the circle area thing. Yes. Right, sorry, yeah. Good. Right. Okay. What are we doing then? Might be one of that 1, 3. So, well, yeah. Okay. There was a GCSE question with a lot of circles in. Right. Okay. I've maybe reminded people of bad times at a GCSE exam. I'm sorry for that. Yes. Right. Okay. Here we go. Chat's joining in. Chat would slightly hide the question, I think, but I'm just going to read out chat messages. Bayer in chat. B in chat says use the fact that the angle at the center is twice the angle at the circumference, which is all-timer triangle fact, I think. So if I label these A, B at the top, and C, angle ABC, then this angle up here is doubled over here, which is interesting because, well, we could play that game for the other angles, and we would get 3 of these things at the center. Could do that. We can think about gaps. Ooh, possibilities congruent to the triples that sum to 9. Really quickly, I think we know this angle at the center with A and C positioned as they are, just because, well, perhaps you know about clocks, but perhaps these points are equally spaced, right? So if I count around the circle, 1, 2, 3, then that's 3/12 of a circle. So actually, I think that's a right angle in my current picture. Right, triples that sum to 9. Triples that sum to 9. What's that? Think about the gaps. So I think the gaps are relevant because the gap between A and C controls how large that angle is, which is then twice as large as the angle at B. Yeah. So I know angle AOC. Right. Okay. So angle AOC it is 90 degrees, but it could be. And if you're playing along at home, you should probably now list the angles that it could be. I mean, could it be? It could be, well, A and C could be next to each other, or not. So I think it's 30 degrees, or 60 degrees, or 90 degrees, or la 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 la. And then angle ABC is half that. So it's 45 degrees in this picture. Good to be able to solve it for this particular case, isn't it? 45 degrees in this picture, but it could be. And then other cases, 15 degrees, or 30 degrees, or 45 degrees, or okay. And if I put A and C really close together, then I really can make 15 degrees. Question, I suppose, is how far does this list go? How can we go? Do we use modular arithmetic? I think not unless you really want to. Is the center 0, 0? It can be if you want to. And these are good questions. Let's put these on screen. Look at this. Is the center 0, 0? Yes, if you want it to be. You can choose. If it doesn't say, you can start your own coordinate system, starting wherever you like. For me, I always start my coordinate system starting on my own face because I believe that I'm the center of the universe. So for me, it's not at 0, 0. It's about 1, 0, right in front of me. But you could start yours at 0, 0 at the center of the clock face rather than the center of my face. I should have done relative coordinates on the screen, say like -10, 2 or something. Never mind. Right, okay. So I've got lists in chat of things separated by 15 degrees. Question, how far can you go? And do you have to stop? So Martha stopped at 90 degrees. I can definitely make 90 degrees if I put A and C on the diameter. Can you make the angle at B obtuse? So Sebastian agrees with Martha. Sadler's disagrees. Extremal combinatorics has got, what is that? Stopping at 90, I think. So it's like, okay. What if ABC are adjacent? Yeah, okay. So Matthew L has got a particular case. 12 o'clock, 1 o'clock, and 2 o'clock. In that order. Yes, right. I should try and copy this picture, shouldn't I? I've done such a good job of drawing that. I'm going to try and copy paste it. Different case. Okay, here's another case. Oops, slightly off screen. There we go. But I'm going to try and move it around. I want to do the 12, 1, 2 thing. I'm going to move A and C all the way up. Am I? Yeah, no, this is a great idea. I should definitely try and draw this picture. It's part of the question, isn't it, to try and draw the picture? So I erase that, I move B, oops, move B and C and A. So chat has decided, I think, that if you move A all the way over here, sort of approaching B, then the angle in a semicircle is a right angle, so you can make 90 degrees. But then question, what happens if you keep moving A around? So you get even closer. And I think that makes an obtuse angle. So I think that's slightly larger because the angle at the centre, this is complicated perhaps. Maybe when you learned about angle at centre it only went up to 180 degrees. But I think the angle at the centre fact is still true, even in this case. So slightly wonky picture. I'm going to briefly delete the line AC so that we can see more clearly what's going on. Slightly wonky picture, but here I've got an angle at the circumference and an angle at the centre, and I claim that this angle is still doubled at the centre, even though 2 alpha is now bigger than 180 degrees. If that's controversial to you, then you can prove this fact using your normal version of angle at the centre and your knowledge about cyclic quadrilaterals. So drawing some sort of cyclic quadrilateral, woof, look at this angle over here, pow, look at the angle at the centre, zap, come around to the other side of the point. Chase the angles all the way around, and I think you get a factor of 180 degrees, 360 degrees, subtraction cancels, you get exactly double the angle. You can chase it around. So it's still true, even though it goes past. Isn't that nice? Which means you can keep going. Oh, good. Somebody chat agrees. Yeah, so you can get all the way up to 150 degrees if you move C up as well. Move C all the way up here. All the way up to 150 degrees, where this angle is enormous. It's 300 degrees. So that angle there is 150. A kind of wedge of the circle formed by the arc AC might be huge. Okay, so I think you get all the way to 150 degrees, but I think you can't do 165 degrees. There was a question in chat a moment ago, would I expect answers in radians? Either are fine. I personally prefer radians, but I do all of my thinking in degrees. That is a conflicted personality, I think. Some people only use radians fine. TMUA questions are written either in degrees or radians. It depends on the question. So we all have to learn both, I suppose. Right, can the angle 0 be A, B, and C? So I say that's 150 because it's half the angle at the centre, by the way, for anonymous person at the top. The angle at the centre is 300 because it's 10/12ths of the circle. 10 points round on the clock. And then half of 300 is 150. No, stop it with the gradients. I think I can't make 165. Because to do 165, B would have to be somewhere in between 2 points A and C that are consecutive points on the circle. It's possible for A and C to be separated by 11 points on the clock. If there's really nothing, if there's nothing in between, it's possible for that angle to be, I've drawn the centre terribly in that picture, I'm going to have another go. It's possible for that angle to be 330 degrees, but not once you remember that you're trying to get B to be somewhere in between. If you remember that B has to be somewhere in between, then oh no, it can't actually do that one. So this sequence kind of stops. I think it's interesting the sequence stops kind of one early, stops at 150 instead of 165. And I think A, B, and C are supposed to be distinct. And the question says 3 of them are selected. I did think about putting 3 distinct points as selected. I think, who's this anonymous person? Here you are. I'm just going to highlight you. Right, anonymous person at the top in pink. You can check back next year, because next year it's going to say 3 distinct points are chosen, and you'll know that that's because of you. I'm just trying to tell you. In a nice way. That is I'm putting it in there. I'm writing the comment. distinct points. So that I know they're all different. That's your legacy for this question sheet. Okay. Is this the sort of thing you would do at interview or TMUA? I can imagine this being TMUA, sort of. If it's interview, then I don't really have a follow-up. I don't really know what I'm doing with this. I like my interview questions to have like somewhere to go, so that if you do it really quickly, I can ask you a follow-up. I don't quite know what that would be for this. I guess I could start asking about the average. If you choose A, B, and C at random, this is my if in doubt, start asking things at random, right? Ask if you choose A, B, and C at random, but then awkward. What's the average angle? Is that interesting? Not that interesting. I think I just all worked out how I would whatever. Okay, maybe. For some of the TMUA questions further down, I've been trying to think of ways that I would use them as the start of an interview question. I don't actually do that. I should be maybe clear. But for some of the TMUA questions, I need to write extension material, and that thinking of extension material is also kind of how I try to think about interviews. Not just what's a good idea for a question, but also where am I going with this? What am I trying to achieve? The one that I used last year, I'll show you at some point on this show, I think. I had about 8 parts or 8 things I was planning to do. Like, so 8 points where I thought that would be a sort of acceptable place to stop. So if we run out of time, that's kind of a stopping point, which I liked having. Rather than just like one idea, to have like 8 ideas in a row. Interview questions are hard. Hard both ways around. Anyway. Instead of saying the angle at the centre is the arc length, an angle from the circumference of a unit circle is the Instead of saying the angle at the centre of a circle is the arc length, then an angle from the circumference of a unit circle is the arc. I don't think I say either of those. Fair enough. B can't go between A and C if A and C are consecutive points on the circle. All of these are supposed to be chosen from those 12 equally spaced points at the question in the top left of the screen. Yeah, sorry, that's one of those points where I've remembered something from ages ago about the question, didn't draw attention to it, and just used it without saying. I need to get better at that. Okay. 8. Let's go for 8. Are we starting a thing? Oh, justice for gradients, but no thumbs ups. That's pretty. Oh, but below you gradients to get to, so you know. Okay. Oh, I see. You're into double gradients. Oh, it's like it's an extension of the gradients chat. Sorry, got it now. Different angles. Slightly different from gradients. Possibly in the way that pi and 2 pi are different. Okay, fun times. Right, question 8. It's also got a bit of a trap in it. Let's have question 8 on screen. It's up there. 8 comes before 9. Question 8, people want to talk about. This one's I never say trick question, but this one does have something going on once you draw a diagram. So 0 and then the bizarre coordinate a plus 1 over a. So what on earth is going on there? I have like alarm bells for what? And then 1 comma a. So that's like somewhere over here. So it's drawing it. Yeah, let's go. And those are on a circle. There's a word for this when you have a triangle and you draw a circle that goes through all 3 points. You can always do it. I don't think it's on GCSE or A-level maths for you to know that fact. But hey, here we are. Here's 3 points going through this circle. In particular, it would be nice if we knew any facts about this triangle that we've got. I'm going to draw in the triangle. Because if we know about the triangle, then maybe we know about the circle. So I suppose I'm looking for facts that combine triangles and circles, and I know a couple. I mean, I know that alternate segment one, but I don't have any tangents. Some of the ones about angles above a common arc feel like they have a triangle in. It's not a million miles away. Yes, it's called the circumcircle. Right. I think this really comes down to trying to work out perhaps the lengths of some sides or the values of some angles. We're just trying to get to grips with what is this? Where has this come from? One approach is to write down things in terms of vectors, although that's not what I want to do because I've realised that that uses weird vector facts, which I shouldn't say. Yeah, so sort of you have a nice surprise, I think, if you try and find the lengths of each. So this is root 1 plus a squared. This is root 1 plus, and then the difference here is 1 over a. So that's already a bit of a surprise. And then this is, well, hang on, this is just a plus 1 over a. Is a positive number? I should probably say that a is a positive number. Anyway, so this length is a plus 1 over a. I've written that really badly. There we go. A plus 1 over a. So then the surprise from the cosine rule, I think, is that if you square each of these and add them, you get the square of this one. Because you get the 1 over a squared, you get the a squared, and you get 2 from adding together these ones, which is exactly what you'd get if you squared this. Which means, we have a right angle triangle. Yes, Anonymous in chat says if it's a right angle triangle. Extremal Combinatorics says right angle triangle. Modus ponens, it's a right angle triangle. There you go. And that means that the hypotenuse is the diameter. So the circle has this as the diameter. Surprise! A completely unreasonable thing to sort of guess. But if you have this idea that you might mess around with some triangles, try and work out facts about the triangle first, then that helps you work out facts about the circle. I think this is probably the hardest question on the revision section. I don't even know if it counts as revision because, well, would this be on GCSE or A-level maths? Probably not. There's a circle that goes through all three. If that's the diameter, then the midpoint is halfway up. The midpoint's halfway along in diameter. So what's the question? Find the centre of the circle in terms of area. It's like halfway up. So divide that number by 2. Yeah, it's just second midpoint. You could work out gradients of lines. Yes. You could work out the gradients of the lines. Brilliant suggestion in chat. Anonymous person. So the gradient of this first line, let's do green for this first line, has gradient A, because it's gone up by A units in the space of 1 unit. And then this pink line going down has gradient, a bit complicated, but it's lost 1 over A in exchange. The change in rise over run is minus 1 over A over 1. So this one has gradient minus 1 over A, and oh my goodness, these things multiply to minus 1. These are perpendicular. I think finding the gradients of lines is one step more removed from circles and things. So if you thought of doing this, good job, well done. You found a way to prove that these things are at right angles. Well done. I think it's harder to think of this than it is to think about triangles, which is why I've framed the bit on the left as, hey, why not think about the triangle before you think about the circle? But I think that is really tough. We're going to have a quick look at 6, and then we're going to take what the World Cup are calling a hydration break. And then, yeah, then we'll do some TMUA. Yes, there we go. So, sort of mad question there, sorry, for question 8. Let's have one more look at it. Because it looks absolutely impossible. And in general, that question kind of is absolutely impossible. Given 3 points, find the centre of the circle that goes through all 3. In general, the question is kind of too hard. I mean, it has a solution. It's uniquely defined by the 3 points. It's not a very nice formula. But here, for this special triangle, you can do better because the triangle is right angled. So you can say what the centre is. Right. Speaking of things where it's really difficult in general, but not so bad here, this is the situation that I was describing before for question 6. If I scroll up so that you can see it as well. Question 6, where 2 circles, each of them has their centre on the circumference of the other one. How do I know that? partly because it's my question, and partly that's very cheeky of me, isn't it? And partly because we know where everything is. The first one is just definitely a circle of radius 2. So I'm already thinking about the radius being 2, and then I see the equation of the second circle, and yeah, there's the number 2 in there as well for the x coordinate. Where is the centre of the second circle? If this is 0, 0 and radius 2, well, the second one is at 2, 0, which is on the circle I've already drawn. So for my second circle, which seems to also have radius 2, I should line the centre up and put it directly through the point on the circumference that I've already got. So that I've got two equal-sized circles. I'm going to draw some triangles. Equal-sized circles. Off we go. Now, Martha put something in chat ages ago to say that you could do the areas of segments. I think that was about this calculation. So here we are. There's this classic way to find the area of this sort of shape. I'm going to colour it in green. So this sort of shape, which is not a sector of a circle, but you can make it out of a sector of a circle minus the area of a triangle. So this is the strategy that I've seen several times for pictures like this, which is green plus pink. These things together make a sector. In this case, it's 120 degrees. It's 1/3 of the circle, which I know from thinking about equilateral triangles, see previous. By Gingerbread. Yeah, so you even find the point of intersection. Thank you, Anonymous. It's at 1, square root 3. So if you like, you could even check that that is really on both circles. Is that a previous question? Maybe not. Find the length of... Yeah, so question 5 is supposed to set you up for this because... let's scroll a tiny bit. Question 5 is supposed to set you up for this by saying... these are points A and B. You don't realise that when you're doing question 5, of course, but it turns out the angle is 120 degrees, so this is more or less angle A and B. And then in question 5, you're asked to find the arc length and the area, green plus pink, of that sector enclosed by the arc and the radii. It's 1/3 of the circle, so 1/3 of 4 pi, I guess. Okay. That's green plus pink. And then if I just want green, I should subtract the area of the pink triangle. So quite often people do this kind of like sector minus triangle approach. If you want to find the area of something like this, where you've taken a circle and you've sliced it, but you missed the middle. Whoops, you missed. And you've got now a little bit over there with an area that's not half the circle because you missed the middle. It's a bit less. People do the sector minus triangle thing. Yes, okay, so you've got two equilateral triangles in there as well. Although if you want all of the area that's inside both circles, you also have like these little bits. It's not just the equilateral triangles, but you have got a couple of equilateral triangles with side length 2 in there, correct? Yes, good. Okay, I can't remember the number at the end. I'm not going to complete this calculation, I think. I'm going to leave it there. And 7, I'm going to show you the graph using my show you the answers technology. Let's have a quick look. So if I do this, and I believe we are now looking at the solutions. So down here, I've got the diagram there, the points of intersection. Oh, I did say find the points of intersection. Why did I do that? Don't know. I appear to have used some terrible geometry to work out that that's 120 degrees. What a terrible solution. No, this seems fine. Okay. And then 7, I want to show you this graph. So cheating a little bit, here's a plot of the graph. So what's the setup here? Let me just reread the question. So this is a circle with centre C, 0. So it's moving the centre of the circle, C, 0, and radius 1. And the area that's in the region x greater than 0. So as C changes, the circle will move to the right-hand side of the plot. How much of the circle is in that region depends on C. It's an area that depends on C. So it's 0 if C is small, because the circle hasn't got to the right-hand side of the space yet. And if C is greater than 1, then now all of the circle is in the right-hand side. Should I have a diagram for this? Oh, I could go split screen, couldn't I? I could go split screen. Maybe that would be more fun. Let's go split screen. So x equals 0, start line, circle, perfect circle. Radius 1, and circle is moving. So to start off with, the area that is in x greater than 0 is nothing, but then there's a bit where it increases, and I think it increases slowly and then faster, because as C changes, larger slices of circle are going past. If the circle is made of cheese, and we are slowly pushing the circle through, then I'm getting larger slices of C, cheese, near the middle. Why did I go for cheese? And then after the halfway point, the circle moves a little bit, and I get a bit more circle on the right-hand side, but smaller this time. It's not as big as the slice I got before, and then it moves a bit more, and that's not as big as the slice I just had. So the amount of circle on the right-hand side is still increasing. I'm still gaining circle on the right-hand side, but diminishing returns rate, slowing down until here I'm only being given a little bit more circle at all. And then worse, I've got all of it. And the C keeps increasing, but the amount of area doesn't go up beyond pi, the area of that circle. Right, why did I pick cheese? There was a moment in there where I really thought I could maybe do a good explanation. It came and went so quickly. Right, let's reset this. Was that the question? Yeah, so it's not quite, that one is not quite, yeah. What is that one doing then? So this is my attempt to ask yet another question about areas where you slice a circle and you take some of the area. And yet again, it is not a simple calculation. So I'm not making you calculate that thing in the picture at the top. But, you know, yeah, could do something like this. Okay. Right. Now what? Right, we've hit 6 o'clock, so I think I'm going to drink water and look away from the screen for a second. If you have been staring at a screen for the last hour, you might like to also remind yourself that you can look at things other than screens. Looking at something distant from a screen is maybe good for your eyes. Oh, goodness. Also, it means you're not looking at the maths, or worse, me. Right, okay. Right, back in. Hello. How's it going, chat? We all right? So Sky is saying something about sin x between 0 and 90. This is what we're going up and then down again. Maybe that's the rate. I think it's worse than sine. There's some sort of compound thing. If you do this calculation in general to find the amount where the circle is like halfway, not quite halfway, sorry, then you've got that kind of region where, yuck, the formula for that area is pretty bad. In general, you have to do something involving working out the angle at the center in terms of C, which is pretty bad, and then converting that angle into, via the sort of calculation we were just talking about, the area of that bit of the circle. Yuck. Okay. Calculation that people don't want to do. That's too silly for me. Right, okay. I think it's time for some TMUA questions, which means I need to flip the screen over, having just reset everything nicely, to get this back again, so that I can, there as well, so that I can see what I'm doing. Gosh, it's not a great setup, is it? There we go. Okay, I think I'm back to questions. And I can now scroll down to TMUA, and we can do some voting for TMUA questions. It is so warm. Yeah, you could integrate 1 minus square root and 1 minus x squared root. Oh. Is it all right if I say that I don't want to? Like, you kind of, the thing at the, yeah, right. You can't do it using TMUA methods, if anybody's wondering. That's not something you know how to integrate for TMUA. TMUA only requires you to integrate polynomials. Is that true? We've got an integration session coming up in a couple of weeks. Maybe I shouldn't improvise. Okay, TMUA questions on screen. Let's have a look at what we've got this time, and I'm going to switch on another vote in chat. This is a vote for the 6 TMUA questions that I've selected. You can choose what we're doing next. Here they are, and I'm going to talk about them a little bit. Anyway, here's a question with 2 circles where we're asked about a line that is tangent to both of them. Maybe you want to see that one, or maybe you want to see this equation, which, oh my goodness, involves loads of logarithms. Logarithms are next week. No, wait, logarithms are 2 weeks from now. So if you haven't seen logarithms yet, join us again in a couple of weeks to learn about logarithms. I think the hints for this question just say, let's see if we can find them. So the worksheet comes with hints as well. The hints for this question just say, if you haven't seen logarithms yet, come back to this question after you have. It's really not worth thinking about until then. But at least when you see the question, it's kind of clear that that's really what. Some votes for this one because I think the answer is surprising. I think the question is. It's weird in that way that I've kind of already mentioned where you have to remember a thing from the start of the question when you get to the end of the question. Memory test in a way. 3 has got so many options. Look at these 8 options. Lovely. This is basically a calculation question, but they've thrown in options G and H just in case. When I was at school, I did a lot of UKMT challenge questions where occasionally there'll be a multiple choice question on UKMT which said sort of 4 options, and then final option, there is not enough information. And I don't know, maybe there's sort of urban legend or something, but as far as I could tell, it was never the right answer to pick not enough information. TMUA is a different test, and it's in some sense a bit harder, in some sense a little bit more into that sort of thing. So it could be. But my personal bias is that unless I'm really confident, I'm not going to pick options like G and H. They just seem too weird to me. Maybe that's my personal bias and not actually great teaching or whatever. Some people are voting for it, so there you go. We at least mentioned it. My strategy for this question is to calculate unless I get really, really confident that it's not a calculation question. Okay. And then this one is about similar sectors of circles, which I'll admit was a new concept for me when I read the question, because I'm used to similar triangles. Can sectors be similar? I guess maybe similar just means scale factor, right? Maybe it just means that you can scale one and get the other. That'd be fair enough, I suppose. In this case, you kind of try to turn this into an algebra question as fast as you can. Really as fast as you can. At the moment, I think 4 people have voted and you've all voted for different questions, so that's kind of fun. We're going to leave that boiling a little bit. Hints. And we've got this question about, so this is about maximising the area of a triangle. I'm very keen. I love questions where you maximise the area of a triangle. We're given some facts about triangle POQ, including its area, which is a bit of a surprise, and this weird fact that its angle is greater than or equal to pi by 2, which, bit of a surprise. And we're asked to maximise the area of triangle PRQ. So we're going to need a really good diagram for this. Maybe multiple diagrams because we're thinking about different cases. So it's something going on. And then 6 down here is the kite question from sort of trailed earlier by us talking about parallelograms and kites and GCSE level maths. GCSE level is not a great. I don't mean that. Okay. And the question goes, oh my goodness, which of these is necessary and sufficient for the angle SPQ to be a right angle? When they say necessary and sufficient, they just mean enough and needs to be true, which here sort of just means we have to do the question properly. It's not enough to just come up with some condition which says, it would be enough. If everything were equal, that would be enough. It's got to also be necessary. Mathematicians use words like this to try and capture the idea that you've not lost any information and you've not gained any information, and that you have things that are actually equivalent. That whenever this happens, that happens, and there are no other in-between cases. Right. Okay. How's the voting going? Let's have a look at the voting. The options for this are pretty nice. Squares, factors of 2, x, y, and z all equal. Maybe that's enough on the left, but that's quite strong, right? The one on the left has got 2 equal signs in. It kind of feels like a lot of condition. Maybe too much. Maybe it's sufficient if you do all this. That's enough, but you don't need all that. Right, voting on screen. People are currently voting for the very first question we saw back there, the very second question we saw. So circle questions at the moment, and question 4. Is there a theme there? Yeah, they all involve circles, but there again, most of these questions do. Yeah, all of these questions involve circles, including secret circles. Spoilers for circles. Question 1's just nudging ahead a little bit there as one more person votes. I'm just going to have a quick look at chat as well, see if anyone's telling me about chat. Ritvik agrees with me that it's never none of the above. Do I know any resources for practicing calculus in bulk? Depends what you want. I quite like the kind of free online textbook stuff. There exist resources. If you just want a bunch of integrals, then it depends how hard you want the integrals to be. There exist things like integration B if you want some really hard integrals, but you've said bulk, so I think you're trying to do normal integrals. And there are resources for A-level students out there on the web where it's just like a worksheet with 100 standard-looking integrals. You just calculate lots of stuff. The challenge there is always going to be that the questions that you find will all look quite similar because they're all integration. But it's going to be hard for you to tell when you look at the questions whether they've been written for people who know the same mathematics content as you, because a question that uses integration by parts looks very similar to a question that uses integration by substitution. And if you don't know what either of those are, then how are you going to tell? Because again, calculus is hard like that for that reason. Just recognizing whether the questions are appropriate. If you've done a particular qualification and you're looking for questions that are like that qualification, you could go check. And if you're thinking of a particular topic, although of course the problem with Googling a particular topic is that you know how to do the questions before you've even seen them. So if you search for integration by parts, tricky questions, then how tricky can they really be? Right, okay, 1 and 2 are really winning this vote, so we're going to try and do those. And I'm going to try not to talk too much about questions 1 and 2, because I would also like to try and do question 4, which I have over there. Okay, so let's set this back. Sometimes my stream setup feels very magical, you know, I can have all the different things on screen all at the same time, and sometimes it's just really clearly me scrolling through a PDF, right? There's no magic there. Okay, let's put that on, let's switch chat off, let's have, one day I'll be able to do that without saying it out loud. Okay, and let's stop voting. Okay, I'm going to stop looking for yes, suggestion in chat for maths, good stuff, hard stuff. Reese would like to know where to find the revision sheets. Everything is on a single website, which is linked on screen on the purple bit just here and in the YouTube description if you want to grab that worksheet that I'm scrolling up and down, or the solutions worksheet, which sometimes appears on screen in a way that seems quite stressful for me, but you could be just relaxed looking at the solutions right now. This stream is not really about just getting the solutions right. I'm supposed to add some element of discussion or chat. Well, let's see how that goes. Okay, so 2 circles in this question. Let's do it chat style. I think I can fit chat on the screen as well. Chat, you're coming back. There you are. 2 circles in the question. What do you notice about those circles? Am I on the right bit? Yeah, I think I'm on the right screen. Don't panic. There we go. 2 circles. And like multivariable calculus has turned up in chat. Thank you. Good username. There are several things you might notice about these circles, and I'm kind of interested to know what order you spotted them in, or which ones you've spotted. They are x plus 2 squared plus y minus 1 squared is equal to 3, and x minus 4 squared plus y minus 1 squared is equal to 3. What do you notice? Aha, right, okay, so responses coming in chat. Yeah, so same y coordinate for the center, same y center value and radius, says Sky. Same y, same y transformation. I suppose if you think of these as transformations of your favorite circle, then sure. Martha's telling me about the radius. Multivariable calculus says same radius, same y value for the center. Yeah, okay. This is good. We should probably think of this sort of thing before we try and sketch the picture, right? Because if I sketch a picture and I draw two random circles, then they go, oh yeah, actually they're supposed to be the same size. That matters quite a bit for, well, my ability to do this question. I'm also going to use the circle tool because I can. I've learned the shortcut for it now as well. Okay, so two circles that have the same radius and same y coordinate. Look, it lets me do that on the whiteboard. That's nice. It lets me line it up. I can change the font size as well. Good times. Same gradients. Interesting. Tell me more about the gradients. So gradients, I think, is probably not a fact about the circles, because a circle doesn't really have a gradient. But you're already thinking about the straight line L, which is tangent to both C1 and C2, and has positive gradient. So Anonymous is telling me about same gradients. You're moving on to talk about lines. Let's go. It's not as gradient. It's slightly underneath the chat, but it says this line has positive gradient. Full stop. Right. If they have the same tangent, they must have the same gradient, I guess, at the point where they meet the line. Yeah. Although a circle's like a rainbow, right? It's kind of got every value of gradient. Any circle you think of, there's somewhere on that circle with the correct gradient for any given line. That sounds really profound, I think, sort of, maybe, but it's just because the circle goes all the way around. Sorry, I'm really... If somebody's watching this video back in, I don't know, October, November, I need you to know that it is currently very warm. Right, okay. I'm struggling, but we're going to be all right. Should we draw the x-axis? I've got a better idea. Using the corresponding angles or something, which is that y transformation, right? They've both had the same y transformation to bring them up by 1 unit. So what means that I want to draw the line y equals 1 and think about angles where things meet the line y equals 1. Because, well, L fine. The angle where you meet the x-axis is the same as the angle where you meet the line y equals 1. So anything that crosses this, I'm going to try and draw a tangent. Whoa, not quite. The angle where it meets like the x-axis down here somewhere is the same as the angle where it meets line y equals 1. And the line y equals 1 just feels more relevant to me. Just more like it's related to what's going on in the question. I don't know. We've got a choice. Right, okay. Y is 1 plus square root 3 and y is 1 minus square root 3. If you make a rectangle out of 2 lines, diagonals are also... Right, okay. So if you put... Ooh, okay. So 1 plus root 3 would be this top point, I think. Like the tops. And then some rectangle. Although I don't think the line's going to be tangent at the top. There is a line that's tangent at the top of each circle. But I don't think that's got positive gradient. Just because I don't think 0 counts as positive. We've got a line that's tangent at the bottom of the circles as well. Has that worked? Oh, yeah, good. So is tan theta not just the gradient? Yeah, tan theta is the gradient of the line. What's the question one? Oh yeah, okay. Should we talk about that? We can talk about it. Okay. So, facts. For a straight line, the angle it makes with the x-axis is tan theta with, surprise, the gradient is tan theta. That is just a fact about straight lines. Proof, I don't know if you'll like this proof, but where it meets the x-axis, you can draw a little triangle. It's a tan theta thing. I always want to draw a little triangle, right? You draw a little triangle going across by 1 unit and up by m units. If you do that, that's definitely the gradient is m, but also, what's this angle going to have? That angle's going to have tan theta is equal to m. So there's a sneaky way to translate between gradients and angles. If you want to. No one can force you to. You don't have to. Right, okay, Martha has gone off the idea of these top points on the circles, fine. I worry a tiny bit that Reese is planning to solve for the equation of the line, and that is actually quite hard work. It's doable, you can do it. We did something similar, was it last week or 2 weeks ago, where we had a pair of parabolas, no, a pair of straight lines, and we found a parabola that was tangent to both. The maths, which was quite hard there, you can do it here as well. So you have like some line, and maybe you're already off and away. Maybe people are going for it. You could write down your equation for the line. We'll call it mx plus c. It's a good strategy. Write down the equation. We've got two unknowns, m and c, and we've got two facts. It's tangent to the left circle, it's tangent to the right circle. Oh my goodness, what does tangent mean in terms of equations? I throw to chat, I think. Where am I going with that? So I've got the equation of a line, I've got the equation of a circle, and I want to try and capture the idea that the line is tangent to the circle. It meets it, doesn't cross at two places, it doesn't miss the circle, it's just tangent to the circle. What does that mean? So I've got something like y is mx plus c. Yeah, Sky did some circle theorems. Oscar's telling me radius and tangent are right. Yes, okay, right angles, points of tangency, angles, nice. Probably the same circle theorem that Sky wants to use at the top. And then midpoint of the centers, yeah, okay. Some nice symmetry thing. Yes. What's Sebastian saying down there? Sorry, I've just lost that with the bottom of the screen. Right, yes, important fact, which actually I think somebody else told me earlier as well. The circles don't touch or overlap because 6 is large and 2 root 3 is pretty small. I've taken that for granted, but it is part of my picture, isn't it? I've drawn these two circles miles apart. Fair enough. Okay, Ritvik says, right, okay, so you could plug in y equals mx plus c into these equations and use the fact that each of them separately has discriminant 0. They have a repeated root. That repeated root corresponds to the point of tangency. You could go and do it like that. I'm not going to suggest that you do, because that's pretty hard. Okay. I like this idea in chat that I'm not going to divide by 0. Boo. I like this idea in chat that the midpoint of the centers, there's some rotational symmetry going on, and that this line that I'm trying to draw that's tangent to both circles will sort of magically go through that point in the middle as well. It'll be over here somewhere, it'll be tangent to this circle, it'll come up, it'll cross this line somewhere, we say the middle, and then it'll go and be tangent to that circle over there. I guess people are imagining, if it's not the middle, rotate, and now it's moved somewhere else. That seems weird. There's a unique line that does this thing. It kind of says that in the question, but not in as many words. Okay, let's see if I can draw this line then. So something like this. I have the advantage of this online whiteboard that I can nudge things around a little bit until I've got something where I think that's going through the point in the middle. Don't know if that's relevant yet, but I kind of agree with chat that it's probably going to go through this point in the middle. And then separately, I've got points of tangency, which are not quite the top points. This is not an amazing diagram because those all look a bit similar, don't they? And I'm now colouring them all in the same colour, so that's pretty bad of me, but hey. Points of tangency, which are not quite the top and bottom points. There's a very old step question where that is the killer bit that makes the question really hard. It's about lots of circles stacked together inside a pair of lines, and the fact that the tangency points are not quite where you want them to be is really, really annoying. Okay, the triangle factor that people would like to use, I think, in chat is that there's a great big right angle there, and you know various things. For example, you know this side length, you know that side length over there. Maybe it is relevant where the centre is, where the middle is. Because I'm marking everything in. In some sense, with this coordinate geometry stuff, occasionally you just know where everything is, and it's tempting to just do your calculations using the fact that if you know where everything is, you can calculate any distance that you want, and any angle that you want, any area that you want, really. That's quite tempting once you just know where everything is. There's kind of no mystery about the circles. So if you can relate everything to circles, then, well, you've got to be done, haven't you? Because you kind of know everything. Yes, if you can find the length from the tangential point to the point 1, 1 using Pythagoras. Yes. Yes, I could. Yes, do I want that one? Oh, I do want that one because I want tan theta. Sorry, yes, I do. I need to know this. Is that 4 and 1, so 3? Should probably use Pythagoras then, shouldn't I? So 9 take away 3 is 6, so root 6. Which means that I've got tan theta is 1 over root 2, which is what Reese said down there. I had not already done that by the time I read your comment, but I had marked in the midpoint. Okay, so we've got down to a solution. We've got down to C, I think, in the end, which, fair enough. How much do I care about getting the right answer? I care a bit about getting the right answer, so I have just cheekily checked. People who wanted to do the discriminant, I see you in chat. Let's spend 5 minutes just trying it. Let's see how it goes. Whee. We're going to do 5 minutes. Okay, so rerun, but using this discriminant method. I kind of want to see how much of a mess it looks like. I think it might not be that bad, but it could be very bad. We have first circle, x plus 2 squared plus, and then the equation of the line is y is mx plus c minus 1 squared is 3, has discriminant 0. Ooh, handwriting. So if we're going to work this out, then I guess it becomes something like 4x plus 4 plus, and then over here you need to get this m squared x squared plus 2m c minus 1x plus, oh my goodness, I'm going to keep the c minus 1s together unless somebody forces me to multiply them out. I would prefer not to multiply them out. Right, okay, so already this is looking a little bit bad, isn't it? Because all of the coefficients are messy. Oh dear. 4, I can take off the 3, so at least I get this like 1 plus c minus 1 squared, but I'm not really into it. Okay, so discriminant. This is where it's helpful to remember the discriminant is this thing squared minus 4 times, oh, this is even, which is at least nice. Well, I mean, I could pull out a factor of 2. Maybe I shouldn't say even. 1 plus c minus 1 squared. Do I like this? Not really. Pull out the factor of 2, so get 2 plus m c minus 1 all squared minus, divide by 4 squared 1 plus. Oh dear, and we've got a second circle still to go. So at this point I'm starting to feel like, I can see that the m squared c minus 1 squared is going to cancel, so that's a little bit good. But I still don't particularly love this, the way this approach is going. So minus 4 terms, minus 1 minus c minus 1 squared minus m squared c minus 1 squared, so that at least cancels. And then I'm left with some quadratic for m and c. Do it again for the other one, and then I've got a pair of simultaneous quadratic equations for m and c. Don't love it. Turned out to be loads of work. I don't think anyone in chat was asking me to do that, were they? Okay, right, I'm going to let off the person with username 0, I'm going to let you off this time. Okay. Right. I didn't enjoy doing that, but it only took 3 minutes of my life. If you were watching at double speed, it only took 1.5 minutes of your life, so it could be worse. If you were here live, then maybe you use that as a great time to have another hydration break. Logarithms next. Logarithms next, I think. Other approaches. So it feels like solving for this gradient feels hard. Like solving for the equation just given the facts algebraically seems tricky. So I would not use this method at all if I can avoid it. I will maybe write some of the algebra and then I'd be done. How would I do this in 4 minutes? I would draw the diagram. I would draw the diagram kind of quickly, guess the symmetry thing, vaguely convince myself the symmetry thing is true, and then draw this little triangle. And the triangle's not that bad, right? So once you draw the triangle, I'm invested in spending the next 1 minute actually finding tan theta, but draw diagram. It's kind of a question like, can you process those two circles which look complicated but are actually not that complicated? Can you process that into, maybe you draw a diagram, maybe you find some way to understand it, but can you spot that that's actually a very symmetric picture? They're describing this nice symmetric picture. If you can spot that in under 3 minutes, then you can spend like 1 minute. The actual stuff that you write down is not that bad, right? For actually trying to work out the value of the thing. Like the whole question is sort of, here's a weird setup. It's not actually that weird. I don't know. Right, yeah, it would be more impressive if I actually finished the calculation. And now I'm scrolling past it, so no one can tell me that I got half of it wrong, which could very well be true. Right. It is really tempting to just speedrun, to just be like, okay, here's the question. Let's just do me talking as fast as I can, doing the maths as fast as I can until I wear out the pen. I'm not certain that's helpful. Let's talk about logarithms instead. So I've put it on here because it involves a circle at some point and it involves a bit of arc length fact. But I think maybe obviously the reason that question is hard is because it uses a fact about logarithms. Right, if you've seen nothing to do with logarithms, then I don't watch this bit. Come back afterwards. It's being recorded. If you have seen logarithms, then the thing that I'm referring to is the fact that log x, so log base n thing x, is not defined for x negative. It's not defined in A-level maths or equivalent or on the TMUA specifications. It doesn't mean anything. If you like, this is the fact that powers of 10 are never negative. So if you have the question like, what number do you raise 10 to the power of if you want to get -3? There's no such number. That never happens. Yeah. So here's the next bullet point. You'll notice I'm trying to raise the stakes. 2 log base 10x is not defined for x negative. And then here's the really dangerous bit. Log base 10 of x squared is defined for x negative. Because of course it is, right? Like you take your favorite negative value of x and you square it. Well, now we're dealing with positive numbers. And log base 10 of any positive number is well defined. And you see the problem, right? They're going from this second line to this third line is extremely dangerous, right? I don't know how else to compare this with like square roots or something, where you have something that's like not defined. We need to remember that it was meaningless, didn't mean anything. And then you do an operation to it that's so tempting. It's so like obviously the right thing to do. To move this factor of 2 inside, but that kind of hides the problem. So that's why I'm saying this question is an example of when you need to remember something from the start of the question. We're going to do the algebra, which people in chat are suggesting, aha, combine the logs and you can get the equation of a circle. Right, brilliant. We're going to get to that circle, but we're going to need to remember that those logarithms up there in the question, if in doubt, refer back to the question, those logarithms in the question are only defined if, 3 things, if x is greater than y, if 2 is greater than 2x, and if y is greater than -5. I've said that weirdly. I need the things inside the brackets to all be positive so that those logarithms are well defined. If you like, this is a problem with reversible logic. So you have like, or let's do this like, is -3 equal to 3? Question mark. Idea! Exclamation mark. Square both sides. 9 is equal to 9. Ooh, but that shouldn't be very convincing, right? That we kind of went from a not true fact, but it's really easy to get from not true facts to true facts. Sort of. Yeah. Okay, extreme or common direct in chat gives another example. Thank you. X squared over x is not defined for x equals 0, technically, because you can't divide by 0. Thank you. We're not allowed to divide by 0. But if you simplify it, then you get something that is defined at 0. So it's kind of like doing some simplification might hide a problem. One that comes up quite a lot, I suppose it's got another square rooty kind of feel to it, is square root of x squared. This is a slightly different flavour, but square root of x squared is x if x is positive or 0. It feels like it should always be x, but if x is negative, then it's actually negative x. Because if you have a negative number, then when you square it, you get a positive number. Then you take the square root and you get positive square root. So you get back to that one. Yeah, right. Okay, here we go. Oh, chat popping off with this sufficient but not necessary stuff. Great fun. And complex numbers, which I see the complex numbers. The complex numbers help a bit, but not maybe as much as you want. They don't quite save the day. Okay, let's go 100 like that. Cool. Okay, so let's try doing this question. Yes, that was absolute value of x. Thank you, anonymous in chat. Good. It's nice when you recognise the thing, isn't it? There's a rule. Let's write it in. If you don't like this, you're allowed to always replace it with this. Although I think that that's quite a funny thing to do if you do it all the time, because this is not that bad. Good. Okay. So what next? Right. Okay. That said, so if x minus y is positive and 2 minus 2x is positive and y plus 5 is positive, then we can play. Then we can play. Here we go. So then everything's fine, but I've got to remember that I have those restrictions, right? I'm doing this because I want to try and get rid of the logarithm. So I'm trying to get this together as well. Right hand side also dangerous, look, because if both of these things are negative, then I've gone from a case where in the question it's not defined. So there's no point where not one of the points we're talking about. But if both of those brackets are negative, then I now have something that is well defined because these two negative things are being multiplied together. Okay. So what have I got? 2xy plus y squared. I'm getting rid of the logarithms and I'm multiplying out at the same time. I could maybe do this slower, but I feel like this is not the sort of stuff that people are here to check they're working with. I could maybe get it more correct, couldn't I? Oh, that's nice. 2xy on both sides. So now this really does look like the equation of a circle because I've got x squared plus 10x plus y squared minus 2y is equal to 10, which is one of the forms of the equation of a circle. So I'm going to go i.e. I'm going to put it in my favourite form for the equation of a circle, which is x plus 5. Oh gosh, I really hope I'm getting these numbers right. X plus 5 squared plus y minus 1 squared. So wait, it's not wrong until I write down the right hand side. I can save this. I've got the x squared and the 10x. But at the moment, if I just write down 10 on the right hand side, that's rubbish because I have added 26. I have added 26 to the left. So I should write down 36 on the right, and now I've saved it. It's equal. That is literally how I think about that conversion. I kind of double complete the square. It's like, oh, I'm going to see what I can get away with. Whoops, I've messed it up unless I add something to the other side as well. Right, okay. So circle, but time to remember the if hanging at the top of the screen there. If. So we could draw this circle. It's got center minus 5 and radius 6. Interesting points over here somewhere. But we need to go back and worry about whether these conditions are all true. And these ones turn out to be kind of fine, more or less. It's weird they're strict though, don't like that. So this one down here is y gets all the way down to minus 5 at this point. So this point's not included. And this point over here is not included either, because this point has got x is equal to 1. The centre is at -5, the radius is 6. So the right-hand side of the circle, we get out to x equals 6. X equals 1, sorry. Bother. And that's just the point where this starts to go negative. So that point's not included in the graph either. Right. So I only want the part where x minus y is positive. What about this term over here? And this turns out to be the killer part. Pretty bad. Rivik says helpfully that I can just add the squares on the right hand side. I think that is true. I guess I'm living dangerously by thinking about it every time, and I should maybe calm down and think about things like that. Right, Anonymous wants to draw the line y equals x, the kind of danger line, right? Straight back to the danger analogy. Y equals x, which kind of amazingly, good question writing, I think, kind of amazingly goes through this point and that point. I haven't labelled them on my picture, but it turns out that that's 1, 1, and that's -5, -5, which is kind of amazing. And I want the points, which ones do I want? I want the ones with large values of x. I want x to be bigger than y, which happens not for all of the curve, happens for this part of the curve. Green for good, around this side. Right. I find that surprising. So the answer is part of a circle, but some of this circle is an illusion. Points over here are not really on the equation at the top of the screen there in the question. We've introduced them with our manipulations, if you like. So in here, if x minus y was actually negative, then this logarithm that I've written down on the left would still be the same value. So it's been included, even though in the original question it shouldn't be included, because x minus y being negative doesn't correspond to a real point. So, shall we do the controversial thing? Or we should maybe not do the controversial thing. What time is it? 20 minutes. Right, okay, we've got time to do another question. Very quick bit of controversy. Oh, no one's going to love this. Earlier in chat, someone said complex numbers. What if you use complex numbers? And the answer is that if you use complex numbers, you don't get any in this question. You don't write down any complex numbers. But if you believe in complex numbers, then all of the circle is part of the plot. That if you believe in complex numbers, then all of the logarithms are well defined all of the time, and all of the algebra works. So it's fine, just all of the circle. The answer just becomes F if you simply believe in the complex numbers. Right, that's controversial because it suggests that the correct answer depends on your belief system, which, just to be clear, there are no complex numbers in TMUA. There are never any complex numbers in TMUA. You might know about complex numbers. You can tell that I do, but we must never use any for TMUA questions. Okay, right. Areas. Right. Good. Okay, that is a tough question, right? Because it's asking you to do lots of stuff with logarithms. It's asking you to recognize a circle, and then it gets you if you actually recognize the circle too hard. If you recognize all of the circle, then you will pick F instead of D. And the way this marks is that you don't get partial credit for that. You just get right answers only. Tough. Yeah. So it's a question about whether things are well defined at the top, and that's subtle because you could just define them. I guess we have to remember where things are defined anyway. Right, what's the square root of x squared if you're using complex numbers? That's sort of weird. I think there are also ways to define logarithms such that this question doesn't work and doesn't give you all the circle. It sort of depends what you do. I'm worried that I'm stressing people out by banging on about complex numbers, so I'm going to close a bracket, and I'm going to say that everything in that bracket about complex numbers just now, you don't need to know that. And I don't think I was making very much sense. Right. Okay. Where are we going next? I think we've got one more. Is it dealer's choice? Similar sectors. I think was doing quite well. I'm going to have a quick look at the poll. The only way I know to do this is to switch it on back very quickly. Oh yeah, the poll looks like that, didn't it? Question 4, what was underneath? It's kind of close. Kind of close. Ooh, question 6. Not that many, but okay. Right, no one had time to vote, so I don't think I upset anyone there. Okay, question 4. Ooh, similar sectors. Oh, I do like this. I think this is good. Maybe we've got time for chat to do this question. What do we think? Here we are. We've got 2 similar sectors. Bit fun. What's a similar sector? My goodness. And similar sector. I maybe need to switch off chat. Yeah, we go. You've gone. You're still on my screen. Don't worry. These sectors are similar. The arc length of the small one is 6. That's marked on the diagram. The radius is r. The big one has radius r plus 3. I guess similar means same angle at the center, because the angles in similar things are supposed to be the same. Even if you rotate and scale, angles stay the same. So I think that's what's going on here. The difference between the areas of the sectors, oh gosh, is 21. So we'll need a formula. And then we want the positive difference between perimeters of the sectors. Is this the one where I think in my solution I talked about a strategy point that I think I'm going to hit out loud. Yeah, this is the one where the solution document talks about a time-saving technique. Okay, in this question, time-saving technique, let's talk about it now. You can agree or disagree, I suppose. Personally, I would not try to write down the perimeters yet. I know the whole question is find the positive difference between the perimeters of the sectors. So tempting, right, to just skip to the end of the question, write down perimeters. And first, think about perimeter. What is the perimeter of a sector anyway? And write down the difference of those things, which would be some horrendous expression involving, well, maybe r and theta and 6. You know, some mess. What's theta? That's what I'm calling the angle, I suppose. I would try not to do that yet. And that's a time-saving thing, because there is some possibility that I never get to that bit of the question. There's some possibility that I just mess around with this given statement about areas of sectors. And if I can't get anywhere with that, then I don't want to have spent any time thinking about perimeters. I guess I try to do the first part of the question first and the second part of the question second. Nice to know that we're going to find perimeters at the end. Maybe I read that in the question and I think, I don't know the perimeter of a sector, but I will be able to work it out when I get there. I don't know. What I'm saying is I'm not going to write those things down yet. Chat can agree or disagree. Ordinary judge in chat, when they talk about adding, when Ritvit says something about adding the squares onto the right hand side, they were talking about converting equations of circles. There was something on screen a while ago where I needed to complete the square twice, once for x and once for y. And they were telling me that I could just add 25 plus 1 onto the right hand side, which is the square of 5 and the square of 1. I could be more confident with what's going on. Right, yes, okay, well, let's go for it, because chat is already trying to solve this question. So, yeah, anonymous, Sebastian, off we go. All right, I love it. Okay, how am I going to do this? I think I'm going to scroll down a little bit. I'm going to switch on chat because chat's being excellent. Well done, chat. And I'm going to go like that, but then you can't quite see the options. Okay, this is fine. I have hidden, what have I hidden? I've hidden the options and this thing about positive difference of the perimeters, which I said I wouldn't do yet. So fair enough. So I think we're going to need some equations. And it's usually these kind of questions, another one where we're turning it into algebra. That's the idea, I suppose. So what does it mean for the arc length of the small sector to be 6? Anonymous in chat tells me that means that theta is 6 over r. Or said differently, that 6 is equal to r theta, which is maybe how I might think of it. This arc length around the outside, if you're using radians, it's r times theta. If you're using degrees, then you've got some factor of pi and 180 degrees in there, I think. I don't know. I didn't consider doing that. It doesn't say radians in the question. I guess this is a case where I overcome my thinking in degrees thing to, as soon as I see arc lengths, I would prefer to use radians. Let's make a note. I'm not going to do a poll, but I would be interested if anybody in the chat did this question in degrees. Sort of a choice thing. I haven't really thought about this. Anyway, okay. So this is an arc length fact. Oh, slightly off the top of the screen. Arc length. Do I want the arc length for the other one? No, I want the areas, which is what people are giving me in chat. Areas are, for the small one, 1/2 of r squared theta, and for the large one, 1/2 of r plus 3 squared theta, same angle in each case. And then I would like to work out the difference between those, given, that one's definitely larger, isn't it? R plus 3 is just definitely a bigger number, is 21. Okay. Reviewed in degrees, not fun, yeah. I think those factors will cancel out. I think, maybe not. Oh, yuck, maybe not, because you get some other factors in these area statements as well. Does it actually work? Because 21 is going to be... Yeah, no, it's fine. You'll work out the value of theta in degrees, and that's just okay. Yeah, there'll be a conversion factor everywhere. Okay, yeah, fine. Equation of difference. The algebra is bad. Okay, it's a case where we should probably consider using radians. Let me just try it in degrees so I can sympathize. 6 is, so arc length in degrees is pi r theta divided by 180. I think, yes. I could do with a fair bit more confidence in some of these. I think some of them I just really don't want to mess it up. Oh no, it was back here. Yeah. Oh, I gave you the factor with it. So area is it then 1/2 of, it's sort of the same but with the same factor in it. R squared theta over 180 degrees, which you probably write as r squared theta divided by 360 pi as well, right? Pi, yeah. And 1/2 pi r squared theta divided by 180 degrees. Which you would probably write as 360 actually, wouldn't you? So then the difference of these, oh, and I forgot the plus 3. Oh yeah, okay. I'm going off degrees, I think. Too many factors of theta and 180 degrees. And you could probably tell that I have not memorized these formulas in degrees, which is a personal weakness, I suppose, just in case a question forces me to use degrees and use these formulas. Everything's much nicer in radians. Okay, I'm going to go back to radians. So given this fact, and we know this fact, we've now got simultaneous equations, and my strategy, I think, is just solve. And if I can't solve these, then I want to be able to move on without having wasted any time thinking about perimeters. And if I can solve these, so in fact I can solve these, he says, I'm going to start cheating, skipping to my solutions. I can solve these by, plugging in one into the other. I think it's even nicer than that, because this r squared that you get from multiplying out, r squared is going to cancel with this r squared to give you a linear expression in r. So only one place to replace an r with a 6 over theta, or vice versa. There's only one theta, so things are not too bad. You get a linear expression for r, which means you get one solution for r, unless there's some funny business going on, which I think is 9. And theta is 2/3 of a radian. 2/3 of a radian is, well, some horrible number of degrees, right? Like 360 divided by 3 pi or something, 120 over pi. So then we're looking for the positive difference between the perimeters. The options on screen are lost to me, but that's fine. The options are something like 4.5, 7, 8, 9, 10.5, 14, and that last one, bingo, 15. So if you've got 7, that is one of the options. I think I've got 8, but we'll get there in a second. because I think for me, having solved an equation off screen, it's time to think about perimeters. I don't know if this is a fact that's in A-level or GCSE or something. There's this thing about compound shapes where occasionally you see like a farmer builds a field that looks like this with a triangle and a square. Well, the perimeter of this shape, where you're supposed to go around the outsides. Ooh, the outsides for the perimeter. Hooray! I don't think I've ever seen that for a sector, and maybe I never will again. But here we are, and we've got a sector of a circle. We've got a curved edge, a curved side. Wow! So I think perimeter means we have to go all the way around the outside. So we want something like, if this is R and 6, I think we have perimeter 2R plus 6 for the first one, and for the second one, 2R plus 3 plus, and then that curved side, which is not marked in the question. I'm going to have to use, I guess I could use similar triangles, couldn't I? Or similar shapes, right? What's the scale factor? And the scale factor is something like R plus 3 over R times 6. That's maybe a silly way of doing it. Possibly at this point I know theta, so I should write down R plus 3 times theta. And look, that's of course exactly the same thing because theta is 6 over R. And the difference in perimeters includes a little bit of the difference in both of the radiuses. Because the second one has not just more curved side, but also these radius bits are each 3 longer, which will up the difference by 6, I think, which takes, I think, you up to 13. I'm hoping that I get not too many. Gosh. At this stage, of course, I've got R is 9 and R plus 3 is 12, so I think I know that scale factor is 4/3. So this one along here is going to be, I think, 8. So I have on the left 9, 9, 6 on a curved side, and on the right 12, 12, and what's this? 4/3 is 8. I've managed to talk myself into, on the right, 32, and on the left 18, 24. So I've managed to talk myself into a difference of 8 between those two things, a positive difference in the values of the perimeters of the sectors. So I think this question turns out to be a bunch of algebra to actually write down what you're given, remember some formulas, well, not that. Hey, look, there's the just add the squares moment. Remember some formulas, solve things, given some sort of, I don't know why I was being told about the difference between the areas, and then further on, write down this kind of like what's going on with this scale factor. Once you know everything, you should be able to look at perimeters and things. Review things that maybe the degrees cancel out. If the arc length is x, then perimeters 2 times r plus 3 plus x minus 6 plus 2r. Oh, we see. Oh, that's true. That's a really good point. Sorry. I only engaged with your question on quite a surface level. Does this mean we didn't need to do any of the maths? This is bad, isn't it? Maybe not bad, but wait a minute. Oh, 2 minutes on the clock. Wait. What is this at the top? Should I have just thought about the perimeters? The thing that I said I wouldn't do. I did a big serious thing to camera about how you shouldn't just go and calculate the perimeters. Wait. X is our code for the arc length of big sector. So that's all we want. So then the difference is just this x. But how am I going to solve for that? How am I going to find that? Oh, so this is okay. I think this is okay because now I still have to go and do the rest of the question. Now I'll do everything. So I think you're right. everything above to find theta and r, so that you can work out r plus 3 theta. But then at the end, you get to really neatly calculate, once you found r and theta, you get to save a little bit of time because you can just work out r plus 3 times theta, the arc length of the final thing. So once I've got down to 9 and 2/3, I could just work out 9 plus 3 times 2/3, which is 8. That's pretty slick. I like that. You do need to work out r. You also need to work out theta, I think. Unless there's some magical way that you can. And this does somehow feel like a question where I'm missing something. So possibly, I should go and check the official solution thing just to check I'm not missing a trick, right? You're welcome to go and do that. Go and look at the solutions on the UAT UK website, where maybe they'll have some amazing observation that the difference in areas divided by the difference in perimeters is equal to the sum of, I don't know what, but maybe there's something like that, but not the sort of thing that I can spot. Yeah, you've got to calculate the scale factor, which means working out x, which means working out r and theta. So I think you end up doing the work. So my moment of wait is out, but this is now alternative. It's only a bit alternative because you end up doing all the same maths anyway. Right, okay. That was really fun. Well done, chat. Thanks for joining in all the way through. My goodness, thanks for doing all the voting. We've hit 7 o'clock though, which means that it's time for me to call it a day. I hope that's been helpful a bit. Goodness knows. We've done a few TMUA questions. We've had a good chat about logarithms, which I think will serve us well when we meet logarithms in a couple of weeks' time. All this caution that we might use for logarithms coming around, while still being able to manipulate logarithms and do stuff with them. And I really liked the chat that we had about, the bit where you just went and did the question. Sort of can you do the symmetry? Is it the top points? Is it the side points? How's the gradient work? Could you do it with discriminants? Does that work or not? I liked that brainstorming bit. I thought it was good fun. Right, good. Excellent usernames, everyone. Well done. Right, okay. By next week, next week is straight after the big open days. So possibly lots of new people will be joining us when they find out about this at the open days. But there you go. Is there going to be a stream on logic? We're trying to put a bit of logic in all of them. A little bit, not so much today, perhaps. Necessary and sufficient was in one of those questions. A little bit of paper 2 questions wherever we can. And yes, there is going to be a special session on, we're calling it precision, but I guess that's logic and proof. We're doing that one after the summer break so that you can try some, revising the topics first. You need something to do with all of your logic and proof. You can't just have logic and proof kind of on its own. Well, you can, but not on TMUA. It's combined with other stuff. Good. Okay. Right. Yes. Thank you both. Okay. I should actually stop the show, shouldn't I? Right. I'll be back in 166 hours for more of the sort of office hours of the Oxford Maths Admissions Tests live stream. Till then, have a nice evening. Have a nice weekend. Have a nice week. And I'll see you around. Bye.